We're interested in how we can enable robots to model and influence human teams. An individual can influence teams to do many things, and we're curious whether a robot can also successfully influence teams. For instance, what if this quadrotor wants these group of humans to move toward the red X? Normally, it would need to consider one-on-one interactions with all of these humans. But this approach doesn't scale well with larger numbers of agents. Our goal is to come up with a scalable approach to influence human teams. Our key insight is to use inherent team structures to achieve this. In particular, we focus on modeling leading and following relationships in teams. We propose a way we can combine data-driven and model-based approaches to learn these structures in a way that is scalable with the number of agents. First, we look at the simplest case, where we use a supervised learning approach to model the relationship between two humans. We consider the two-player setting where we randomly assigned leader and follower roles. Specifically, we created a game where we asked two participants to collaboratively arrive at an island. After recording their trajectories, we feed this data into neural network modules that are trained to predict the leader-follower relationships. So in this example, we're trying to predict who Agent 2's leader is. Finally, for each agent, we generate a distribution over potential leaders. This gives us a model that can predict pairwise leader-follower relationships. Now, what goes wrong if we have a much larger team, like this one? Using our trained model, we can compute pairwise weights of leader-follower relationships between all possible pairs of leaders and followers. This method is scalable with the number of agents, since we can easily add or subtract agents without having to retrain our model. Importantly, adding a batch of edges for a new agent merely takes on the order of milliseconds to compute, so we can compute these graphs online. We can then solve for a maximum likelihood graph by pruning the original graph. We greedily select the outgoing edge that has the highest weight for each agent. We are eventually left with a graph where the bold edges represent the most likely edges. Now that we have this graphical representation of leading following structures, how is this useful for our robots? To create policies, we generate this graph every k time steps. We then choose the robot's action that maximizes some reward function defined by the weights in the graph. For instance, if we want an agent to follow the robot would select actions that maximize the probability of it leading the agent, as shown on the red edge. We test our framework in 3 tasks. In our first task, we want to see if we can get the robot to change the graph by making an agent more likely to follow the robot than another goal. Our experiment suggests that with our approach, a robot is able to persuade a human to change leaders much more effectively than a baseline random policy. We also tested our framework in an adversarial task. Here, the robot plans to prevent players from collectively reaching any goal. On the left, a robot using our policy based on the graph representation is more effective than randomly choosing a player to block, which is shown in the middle. Finally, we test our framework in a collaborative task. Here, the robot wants to lead the team to capture the more optimal bottom goal. A robot using our framework is as effective as a ceiling baseline of a robot who heads directly to the target goal. This is a ceiling baseline because teammates have no choice but to join the robot at the goal in order to finish the game. Currently, we're exploring other latent structures that we can model, such as predator-prey relationships. Here, 1 is preying on 2, and 2 is trying to avoid being caught while preying on 3. We can imagine many variants of this predator-prey graph. We hope to learn these predator-prey graphs and design robots that can help capture prey or protect prey from predators. In summary, robots need to interact with and influence human teams, and we provide a scalable approach that learns the internal structure of teams to plan more effectively for robots.